Hi, we're team number 5, and we're going to present you the sustainable process of polyhydroxyalkanoates. What are polyhydroxyalkanoates, or by its acronym PHAS? Hi, we're team number 5, and we're going to present you the sustainable process of polyhydroxyalkanoates. What are polyhydroxyalkanoates, or by its acronym PHAS? A disadvantage of this biopolyester is that it is more costly to manufacture compared to the conventional plastics. In this project, we have studied the process to obtain PHAS from a gram-negative bacterium, Ralstonea eutropha, which is one of the most used bacteria in the production of the biopolyester.
Plastic is one of the most used materials in application as diverse as packaging, medicine, manufacturing, and telecommunication due to its low cost and lightness. According to the newspaper El Economista, Mexico generates around 8 million tons per year and only recycles 32% of the plastic. The development of bioplastic is an important innovation to the plastic industry to achieve a sustainable development. Polyhydroxyalkanoates are one of the most studied biodegradable plastics since they can be synthesized by a different variety of bacteria, as well as renewable sources of carbon and energy, such as fructose and glucose, from agro-industrial byproducts.
The reason why PHAs are also known as polyesters lies in the polymerization of hydroxyalkanoic acids by the action of intracellular enzymes. As we said before, PHAs are polymers of hydroxyalkanoic acids that some microorganisms accumulate intracellularly as reserve material.
For search the correct microorganism, we have to focus in the bacteria because the bacteria have two different things. The first is limitation of the special nutrient, and the second is the limitation is not required of the essential nutrient. For that reason, the pH composition is a high-level variable, determining physical and chemical characteristics of the state sustainable to begin biodegradable under anaerobic and aerobic condition. For that reason, we choose the Ralstonea eutropha, because these bacteria have the ability to accumulate large amount of pH in the interior, in a percentage close to 86% of the dry weight of the bacteria, in a medium from cheap carbon sources such as glucose, fructose, and reduced from the oleic and agroindustrial, among others.
Purified sugars, expensive fatty acids, or edible oils are traditionally used as substrate for PHA biosynthesis, which occurs in most cases as a response to a limitation of nitrogen, phosphorus, sulfur, magnesium, or oxygen, coupled with the presence of an excess carbon source in the culture medium. The selection of suitable feedstock has to be done very carefully because it can impact on the final polymer quality. The cost of the carbon source and raw materials contribute up to 30 to 50% of the overall PHA production cost.
We are focusing on the production from bacterium Ralstonea eutropha, which produces polyhydroxybutyric acid, P3HB. The metabolic process begins from acetylcoenzyme A in a sequence of 3 reactions catalyzed by 4 enzymes, which are in the diagram shown on the screen. The route for the biosynthesis of P3HB shows that the enzyme 3-ketothiolisis is the one in charge of controlling the biosynthesis. And the key to the control of this synthesis in the microorganism is the fate of acetylcoenzyme A, which can be oxidated via TCA cycle or can be served as a substrate for the synthesis of P3HB. The route that acetyl-CoA takes depends on environmental conditions. When the amount of oxygen is adequate, the concentration of CoA is high and acetyl-CoA enters to the TCA cycle while 3-ketothiolisis is inhibited and consequently the synthesis of P3HB ceases.
The raw materials for that process take at place is bacteria, carbon source, substrate, solvents of pH extraction, and the methanol or ethanol for the precipitation. There you can find the flow chart for the pH process. We can identify 3 principal processes. The first is fermentation, recovery, and application. The first is the fermentation, and this is divided in 2 stages. The first is the production of biomass, and the second is accumulation of pH polymer. Second, in the recovery, we have identified non-solvent bases or solvent bases, And then before for the application, we have to differentiate in commodities, pure in composition or coating, and specialties in medical devices, trial symptoms.
General production process is divided in several main stages: fermentation, recovery, and finally processing, starting with the production of biomass from cell proliferation under balanced growth conditions for the accumulation of PHA within the bacterial cytoplasm. Then the PHA is extracted by different purification methods, for example, using organic solvent followed by precipitation, filtration, or centrifugation can also be applied. Finally, the pure PHA product can be applied in different products of pharmaceutic and biomedical industry. Also, they are mainly used for packaging and coating.
This is the process that we have to follow for this project. The substrate that will be used in conjunction with the bacteria for the production of pH is the cassava flour. First, we have to produce the enzymatic hydrolysis and the activation of the bacterial. These have to put on the bioreactor for 48 hours and then pass for the fermentation for 36 hours, and then have to separate the pH for the waste substrate in the centrifugate for 50 minutes.
Solvent extraction is a method to recover PHA from the cell biomass. It is used because of its simplicity and rapidity. Two main steps are involved. First is the modification of cell membrane permeability, allowing release and solubilization. The next step is a non-solvent precipitation. Sulfuric acid is used as a solvent for the extraction and is filtered to remove any type of lipids present in the mixture. And finally, the precipitation is induced by methanol.
You can see the mass balance. We base it on the diagram that I explained before. So we start with some components that we obtain for the papers. For example, the cassava flour, alpha amylase, water, frozen sample of Ralstonia eutropa, culture medium LP. Then we obtain the mix and the feeder of carbon nitrogen, and then we calculate the values of O2 flow bioreaction, O2 flow fermentation, and the sulfuric acid we calculated for the relation between the flow and the acid, and we obtain the waste substrate and the PHA. This is the energy balance and based on the diagram that I explained. So I start with the calculation for the watts that consume the each machine that we use for the bioreaction, fermentation, and centrifugate. The bioreaction and centrifugate is the same machine, and we calculate the total watts consumed, and that is 90,920. For that, I calculate the cost of the energy based on the tariff of CVA, and that process cost 16.91 pesos.
It is crucial to start looking for alternatives of conventional plastics that contribute to more than 50% of the environmental pollution. PHAs can undergo rapid biodegradation from 3 to 9 months. Its production has a positive environmental impact compared to the actual production of conventional plastics. However, the production cost of PHAs is significantly higher than the conventional one.
The overall industrial production of PHA is not viable at the moment because of the expenses that it implies, although the energy and mass balance does demonstrate high feasibility. There are several studies exploring new possibilities for a cheaper carbon source and purification techniques that result in a significant reduction of costs and promoting the application of PHA in different fields and products. Primary sludge and waste-activated sludge from wastewater treatment plants can be used as a main carbon source for the production of PHA. Waste-activated sludge can also be used as a PHA accumulating source, since many bacteria naturally found in this medium are able to accumulate PHAs within the cytoplasm. Therefore, the proposed methodology is a viable and economic option to the actual production process of PHAs. Results demonstrated a total reduction of the production cost equivalent to 19%. In consequence, the final PHA pure product market price is lower and more competitive compared with other petroleum plastics and even some bioplastics too.
There are the references that we use for develop this project.